we again can say that this is a weaker property of associative property. F star G star F is equal to F star G star F. So let's start with the Cayley-Dickson construction. In mathematics, Cayley-Dickson construction, named after Arthur Cayley and Leonard Dickson, it produces a sequence of algebras over the field of real numbers, each with the twice of the dimension of the previous one. The algebras produced by this construction are called Cayley-Dickson algebras. They are useful composition algebras frequently applied in mathematical physics. The Cayley-Dickson construction defines a new algebra by direct sum of an algebra with itself, with multiplication defined in a specific way. There is an involution named as conjugation. The product of an element with its conjugate is called the norm. The symmetry of the real numbers disappear if the Cayley-Dickson construction repeatedly applied. First, we lose order, then commutativity of multiplication, then associativity of multiplication, then alternativity of multiplication, etc. So, if we apply the Cayley-Dickson construction of the set of real numbers R of dimension 1, then we can get the complex number system with dimension 2, and we can see here ordering property of R is lost. Then again we apply the Cayley-Dickson construction, we can get the quaternions denoted by H for Hamilton. It is of dimension 4. We can see here commutative property is lost. In the next step, we can get octonions from quaternions after applying Cayley-Dickson construction, and it is of dimension 8. We can see here the associative property is lost. At the next step, we can get sedenions from the octonions of dimension 16. We can see here the alternative property is lost, and we can go on. We can apply Cayley-Dickson construction repeatedly, again and again. We can see one common thing here: the power associativity remains intact. More generally, we can say that the Cayley-Dickson construction takes any algebra with involution to another algebra with involution of the twice of the dimension of the previous one. We can see here the Cayley-Dickson algebras or Cayley-Dickson construction. The first step is over real numbers. Real numbers are having ordering properties. Then we go from R to C. We lost ordering property. Then we go from C to Q, quaternions or Hamiltonians. We lost commutative property here. Then we go from quaternions to octonions on 8 dimension. We can here we lost associative property, and on 16 dimension we get sedenions. We lost alternative property, and then P Patchen for 32 dimension, X for Chingon 64 dimension, U for Routon 128 dimension, and B for Wandon 256 dimension. So this is all the Cayley-Dickson construction and the produced Cayley-Dickson algebras. This table can tell us a very more detailed explanation in a very brief way. When we apply Cayley-Dickson construction one by one, step by step, we can see here which property remains intact and which property has been lost. If we go to real, as I earlier said, complex numbers complex numbers lost the ordered property, quaternions lost the commutative property, octonions lost the associative property, and sedenion lost the alternative property, and so on. So let's see the way of defining different number systems obtained by Cayley-Dickson construction. First step is the complex numbers. Complex numbers are in ordered pair form. They can be written as an ordered pair of real numbers with addition defined component by component, and with multiplication defined by complex numbers associated with real numbers. With second component 0, the complex numbers are real numbers, and one important operation on complex numbers is conjugation operation. The conjugate has to multiply by that complex number, gives us a non-negative real number, that is called a norm. In this way, we can see that the conjugacy defines the norm, making the complex numbers normed vector space over the real numbers. Multiplication of 2, we are defining complex numbers by Z, that is the ordered pair of real numbers AB. We can see that conjugate Z star is given by A minus IB, and if we do the product of Z with Z star, we can get the modulus value or norm value of the Z. that is square root of z star. And multiplication of two complex numbers z1 and z2 is given as a1 a2 minus b1 b2 plus I a1 b2 plus b1 a2. When we extend complex numbers from real numbers, obviously ordering property is lost. The next step is about quaternions. When we apply Cayley Dickson construction on complex numbers, when we do direct sum of complex numbers to the complex numbers, then we can get quaternions. It is four-dimensional, and a certain representation or a specific notion happening on a four-dimensional sphere being represented in a three-dimensional sphere is called quaternions. Quaternions are absolutely fascinating and often wonder-appreciated number system in mathematics. Just as complex numbers are two-dimensional extension of real numbers, quaternions are four-dimensional extension of complex numbers. Quaternions were first described by William Hamilton and applied to mechanics in three-dimensional space. Quaternions have the ability to uniquely describe any three-dimensional rotation about any arbitrary axis and do not suffer from gimbal locks. You know gimbal locks? Gimbal locks happens because the angles are given in terms of moving axis, resulting in that at certain angles and sets of rotations, a degree of freedom is lost when two angles begin to describe the same axis of rotation. Quaternions have their own very deep study, so let's go in with a very brief. In modern mathematics, quaternions form a four-dimensional associative normed algebra over the real numbers. Quaternions are notated by capital H, blackboard bold H for the name of Hamilton, and for simplicity and symmetry to the other algebras, we are denoting it by capital Q. Here, so quaternion are of the form Q is equal to A plus IB plus JC plus KD, where ABCD are real numbers and IJK are the fundamental quaternion units. We can get any quaternion by the linear combination of the fundamental quaternion units. And each quaternion has an opposite that is called conjugate, and that is formed by negating the coefficients of the imaginary part of the quaternion only. Quaternions has a one real term and three imaginary terms. It is given the conjugate of a quaternion is given by Q star, and that is equal to A minus IB minus JC minus KD. We can get the norm of any quaternion, which is the product of again a quaternion with its conjugate. We can get the norm, and the multiplication of quaternion follows some rules. I square, j square, k square, and ijk will be minus 1. Ij is equal to k, ji is equal to minus k, jk is equal to I, kj is equal to minus I, ki is equal to j, ik is equal to minus j. With these rules, we can get the multiplication of any two or more quaternions. So our next by applying Cayley Dickson construction on quaternions, we can get the octonions. Octonions are also 8-dimensional normed algebra over the real numbers, or we can say that octonions has the twice of the dimension of the quaternions. Octonions was discovered by Graves, and octaves name was given to octonions by Graves. And independently in the same years, the octonions were discovered by Cayley, so that these are also called Cayley numbers or Cayley algebra. We can see the octonions as 8 tuples of real numbers. We can get any octonion from unit octonions by the linear combination of unit octonions. Octonion have one real term and the 7 imaginary parts. Addition is defined component by component, and conjugation is given by negating all the imaginary terms. And again, norm we can get in a very useful way by the product of any octonion with its conjugate. And the multiplication follows again some rules, EI, EJ, where EIs are the fundamental octonion units. EI, EJ will be equal to minus EJ, EI. EI, EJ, EK will be equal to minus of EI, EJ, EK. So with these rules, we can get multiplications of 2 or more octonions. So our next is the sedenions. If we apply the Cayley Dickson construction on octonions, we can get sedenions. These are the 16-dimensional algebras over the real numbers, and sedenions do not have ordering property, commutative property, associative property, also alternativity. It has only the power associative property. The set of unit sedenions forms a vector space of 16 dimension over the field of real numbers, and any sedenion can be obtained by the linear combination of these unit sedenions. As in octanions, sedenion have one real term and 15 imaginary terms. And the addition of two sedenions can be done component wise. Conjugate is again by negating all the imaginary terms. Norm is again the product of a sedenion with its conjugate. And multiplication follows some rules. K naught Ki is equal to Ki K naught Ki. Ki is minus K naught. Ki Kj is minus Kj Ki. And Ki Kj Ki is equal to minus Ki Kj Ki. So by the with these rules, multiplication rules, we can get the multiplication of sedenions. This is the index table for multiplication of sedenions, and 0, 1, 2, 3, 4 are denoting here the index E0, E1, E2, E3 type of things. So let's come to the cryptographic applications of these Cayley Dickson constructions or algebras produced by Cayley Dickson constructions. And for cryptographic applications, we need some basics to know of the type, what type of things we are using. First of all, we should know about the lattice. Our cryptographic construction will contain lattices and their hard problems on which our cryptographic constructions are based. Lattices are nothing but a discrete additive subgroup of Rn. If we are given a basis B having linearly independent vectors V1, V2, Vn in Rn, then the set of all the linear combination of the basis vectors is called lattice. And it is not a lattice of discrete mathematics one. It is a different one here. A lattice can have infinitely many bases, and two bases B1 and B2 are related to each other by the relation B1 is equal to B2 multiplied by a unimodular matrix. Shortest vector problem. In this problem, we are given a lattice and we have to find the shortest non-zero vector. Here, shortest means the non-zero vector that minimizes the Euclidean norm. Since we know that a lattice can have infinitely many bases, computationally it is very hard to find the shortest vector. That's why we use this hard problem for our cryptographic constructions. The second problem is the closest vector problem. In this problem, we are given a lattice and we are given a target vector, which is a non-lattice vector. We are to find a lattice vector that is closest to that target vector. And with the same logic as in shortest vector problem, we can say that computationally it is very hard to get the closest lattice vector to the target vector. This is our closest vector problem. And the next thing, we need polynomials, because we will use the convolutional polynomial rings. So we need to see that which type of polynomials we are using in our cryptographic constructions. So we use ternary polynomials for these cryptographic systems. In ternary polynomials, we have only three types of the coefficients: 1, -1, and 0. Suppose there is a polynomial having b1 coefficients equal to 1, b2 coefficients equal to -1, and remaining are zeros. Then we denote our ternary polynomial by tau d1 d2. Ternary polynomials means coefficients should be 1, -1, and 0, nothing else. Again, we require one more important thing before designing the cryptographic systems. To get a start designing, we need to learn how can we convert our data, which is code for information interchange. After that, we convert the decimal into the ternary representation. We can see it with an example. For example, suppose our data message is hello. Then we can see here, according to ASCII code, H goes to 72, E goes to 101, L goes to 108, second L goes to 108, O goes to 111. And the ternary representations are 72 is 02200, 101 is 10202, 108 is 11000, and 111 is 11010. You can verify it. Now we use a mapping that maps 0 to 0, 1 to 1, and 2 to minus 1, and convert our ternary representation to a polynomial on the set -1, 0, and 1. After this, we obtain our polynomials by assuming that the digit corresponding to 3 to the power k is the coefficient of x to the power k. That means the polynomial corresponding to 02200 is 0 plus 0x plus -1x square plus -1x cube plus 0x to the power 4. And similar, we can do for others. And the first polynomial is P1, second is P2, third one is P3, fourth one is P4, and so on. Then our resultant ternary polynomial is P1x plus x to the power 5 P2x plus x to the power 5 square P3x plus x to the power 5 cube P4x plus x to the power 5 for P5x. Because we are having P5x polynomial, 5 polynomials here. So we can get this resultant ternary polynomial, and we use x with power 5 as variable here because in ASCII code the largest decimal have the 5 ternary digits. Therefore, we are using x to the power 5. So corresponding to the data message hello, the coefficients of the ternary polynomials are 0 0 minus 1 minus 1 0 minus 1 0 minus 1 0 1 0 0 0 1 1 0 0 0 1 1 0 1 0 1 1. So till here we have converted our data message into the form of ternary polynomials. Now again, we need some specific types of rings called convolutional polynomial rings. This is quotient rings of the form R is equal to zx by x to the power n minus 1 and rq is equal to zqx upon x to the power n minus 1. And these polynomial rings are only for one-dimensional crypto application. For higher dimensions, we will replace z of zq by the required algebra required quantities like Gaussian integers, Einstein integers, quaternions, octonions, hexadenians, etc. This is the polynomial representation of a ring element. There is one more thing to know here, named as center lifting. And center lifting means that suppose we are having a polynomial ax in Rq, then a unique polynomial satisfying a dash x mod q is equal to ax with coefficients are lying between minus q by 2 and q by 2. That means we just need to convert our polynomial coefficients between the range minus q by 2 to q by 2. That's all about the center lifting. This is an example. We can see here the center lifting, the centered lift polynomial of ax will be equal to minus 2 plus 3 plus x square plus 2x cube minus 3x to the power 4. We just converted the polynomial coefficients between the range minus q by 2 to q by 2. That is all about the center lifting. So let's start with the cryptographic applications with the help of the previous knowledge. We will see here anti-array crypto system over one dimension, anti-array crypto system over Gaussian integers with 2 dimensions, QT-array crypto systems with 4 dimensions, RT-array crypto systems with 8 dimensions, and ST-array crypto system with 16 dimensions. So let's start. This list is least but not the last. We are going to from reals to complexes to quaternions to octonions to sedenions. So here is the anti-array crypto system. Anti-array stands for the nth degree truncated polynomial ring unit system. It was proposed by Hofstein, Pfeiffer, and Silverman at Crypto 1996. It was acquired by a software security company named as Security Innovation, a software security company, in 2009. This is an open source public key crypto system that uses lattice-based cryptography to encrypt and decrypt the data. And the most important feature of anti-array crypto system is that it is a quantum proof system. It cannot be broken even by using quantum computers. It uses polynomials, rings having integer coefficients, polynomials. And again, we already discussed that the hardness of anti-array crypto system is based on the shortest vector problem and the closest vector problem of lattices. The complexity of anti-array is amounting to big of n square in worst case hardness, NTRU is considered as the fastest crypto system, and its strong points are short key size and the speed of encryption and decryption. It uses this convolution polynomial ring. We can see here the parameters of NTRU. These are capital N, P, Q, D, where N and P should be taken prime, P and Q, and N and Q should be relatively prime. And we are having one more restriction on parameters. Q should be greater than 60 plus 1 P. If this condition does not hold, then we can get decryption failure types of things. And we use here LD1, D2 types of sets, which contains the polynomial of convolution ring R, having D1 coefficients equal to 1, D2 coefficients equal to -1, and rest are zeros. And these are the sets from which we will use our key polynomials. So let's see the mathematical model of NTRU crypto system. In cryptography, every crypto system has, we all know, three main algorithms. First one is key generation algorithm, in which public key and private keys are generated. The second one is encryption, in which the message is converted to a hidden information. Message is called plain text, and hidden message is called ciphertext. The process to get ciphertext from plain text is called encryption, and the reverse process is called decryption. That means the process to get the plain text from the ciphertext is called decryption. In case of NTRU crypto system, for generating keys, the user chooses two ternary polynomials, f from LF and g from LG, and then he computes h as the product of fq, which is the inverse of f under modulo q, and g. He sets f as his private key and h is his public key. Now, in encryption process, to get the ciphertext from the message m from LM, the user first chooses a random blinding polynomial phi from L5 from the parameter sets, and then with the help of the public key h, he computes E as P phi h plus m under modulo q. A is the required ciphertext to which he sends to the receiver, and after gaining the ciphertext from the sender, receiver does some things. For gaining the original plain text from the ciphertext, receiver perform two steps. First of all, he computes fe mod q. After this, he does the center lifting so that a mod q will be equal to a only, and then he can perform the second step, which is b is equal to fp star a mod p, where fp is the inverse of f under modulo p, and the b obtained by this procedure will be equal to m, that is original plain text. So this is the way how NTRU crypto system works. We can analyze the security of NTRU crypto system here from the several attacks point of view, but since we have time constraint and we want to see all the systems based on Cayley Dickson construction, so we will not go to the security part. Apart from that, we can see the real life applications of NTRU crypto system. The Goldberg Messenger was the first chat box and email client with NTRU algorithm under open source license, and it is more suitable to the resource constrained devices, portable devices, embedded systems, etc. It is much favorable to those devices where memory is the main concern. So let's see. The NTRU crypto system is the one-dimensional crypto system. For two-dimensional crypto system, we just replace Z by Gaussian integers, and we can get exactly same type of crypto system over two dimensions. So we can now we will see here the QTRU crypto system, which is four-dimensional. QTRU crypto system. It was proposed by Malikian, Zakir Hosseini, and Mastan in 2009. It is based on quaternion algebra, obviously, clear from name. And in the special feature of this crypto system is that four vectors are encrypted in each encryption round. For the same parameters, we can observe that QTRU is 4 times slower than NTRU, and with the single time parameters, QTRU is 4 times speeder than NTRU. This is a mathematical model for QTI crypto systems. For generating keys, two quaternions having polynomial coefficients f and g from LF and LG are chosen respectively, and the expression h, that is equal to fq of g. Then this capital F is fixed as a private key, and capital H is fixed as a public key. And the after generating the keys, the next algorithm encryption is the encryption can be performed. For encryption, again there is a random blinding of quaternion phi. M is the message quaternion, and the ciphertext quaternion can be computed as P is equal to PH of phi plus M. The next algorithm is decryption. To get the plain text from the ciphertext, again two steps are performed. First one is for computing A, and the second one is for computing B, which is equal to M. Again, after performing first step, receiver do center lifting, and after that he can perform the second step, and he can get the original plain text from the ciphertext. The next one is the OTRE crypto system. It was proposed by Malikian and Zakir Hosseini in 2010. It is based on octanian algebra, and in this crypto system, there are 8 vectors which can be encrypted in each encryption round. And if we want to compare it with original NTR crypto system, we can see that for the same parameters, OTRU is 8 times slower than NTR crypto system. And if we are observing separately, not for same parameters, because here the dimension is 8 times of NTRU, we can see here the OTRU is 8 times speedier than NTRU. We can see here the mathematical model for the OTRU crypto system for the key generation algorithm. First of all, 2 octonions are generated, F and G, where F0, F1, F2, F7 are from the parameter set LF and LG. And then the public key is generated by the expression H is equal to FQ of G, mod Q, where FQ is the inverse of F under modulus Q. And we can set F as the private key and H is the public key. After getting the keys, the user can perform the encryption algorithm. For encryption algorithm, suppose M is the message octonion, phi is the random blinding octonion, and E is the ciphertext. Then ciphertext can be computed as the PH of phi plus M mod Q. And again, decryption contains 2 steps. First one is A, that is F of E of F mod Q. And in this step, there are morphing identities which are used here. And after center lifting, the user performs second step, that is B is equal to FP of A of FP mod P. And if we are going to simplify it, we can see that we can get that these will be equal to M, and M is our plain text octanion. Similarly, the next step of Cayley Dickson construction is to get Sedanians from the octanions, and cryptographic application of Sedanians is the STR crypto system. It is based on Sedanian algebra, and in this crypto system, 16 vectors are encrypted in each encryption round. It is in the similar way. If we are comparing it with NTRU for the same parameters, it is 16 times slower than NTRU. And if we are not taking the same parameters, it is we are comparing it separately, then it is 16 times speedier than NTRU. This is a mathematical model for STR crypto system. For generating keys, we can generate 2 Sedanians, F and G. And as we know, each Sedanian has 1 real term and 15 imaginary terms. And these F0, F1, F15 are from the parameter sets. So we can generate 2 random Sedanians, F and G here. We can compute the product of FQ of G mod Q, and we can name it as capital H, and we can set F is the private key, H is the public key. After getting the keys, public key and private keys, we can do the encryption part. For encryption, M is our message Sedanian, and phi is our random blinding Sedanian. we can get this E by pH of 5 plus m mod q. To Fp of A mod P, that is equal to m, that is the original.
So, okay. So we are very thankful to Dr. Sonika for delivering this talk. And I have some small doubts. Actually, have to get one dimensional, two dimensional, four dimensional, 8 and 16 dimensional algebra. So what is the dimensional algebra? Hello, ma'am.
Yes, sir.
You have given one dimensional, two dimensional, one dimensional is the real number, two dimensional complex, four dimensional, 8, 16, etc. So what is the three dimensional algebra?
Hello. Yes, sir. So please repeat your question.
Uh, Actually, you have shown one dimensional algebra of example, the set of real numbers, two dimensional algebra, and
Sir,
four
this.
dimensional.
Yes, sir.
So what is the three dimensional algebra?
Actually, sir, in Cayley-Dickson construction, we are having the dimension twice of the previous one. So, because I'm talking about the Cayley-Dickson construction, so I'm going to use here the reals and then the 2 dimension, then 4 dimension, then 8 dimension, then 16 dimension, and so on in the form of 2 to the power n.
Yes, yes, this is good. But can you give any example of three-dimensional algebra?
Sir, if you are asking from the Cayley-Dickson point of view, so there are no 3-dimensional algebra from Cayley-Dickson construction point of view.
Okay, okay, okay. And one more thing is,
Yes, sir.
actually you have explained the symmetries of the real field disappear
Yes, sir.
as the Cayley-Dickson construction is repeatedly applied.
Yes, sir.
So first losing order and
Yes,
then
sir.
commutativity of multiplication as well as associativity of multiplication and next alternatively.
Yes,
So
sir.
why are properties lost in the Cayley-Dickson construction?
Actually, sir, when we apply Cayley-Dickson constructions on reals repeatedly, then suppose we are going from reals to complex numbers. So we all know that complex numbers does not have the ordering property. Again, if we are going to quaternions, we can see that quaternions does not hold the commutative property. So it is the feature of that Cayley-Dickson construction. When we perform Cayley-Dickson construction, we there is some property we are going to lose at each step. It is about the construction of number systems because we are doing higher dimensional things. So some properties are going to lose there.
Okay. So from audience, if you have any query, so please you unmute your mic and ask your questions.
सोनिका,
Yes, sir.
इसमें जो तुम्हें E0 E1 E1 7 जो यूज कर रही हो जनरेशन में, ये क्या है?
Sir, E0 even, these are fundamental octonian units based on which we are doing multiplications rules. There are some multiplication rules based on these fundamental units of octanians.
फंडामेंटल यूनिट्स जिस तरह हम लोग उसमें यूज करते थे वेक्टर में 100 और 001 उस टाइप का है क्या ये?
Yes, sir. Yes, sir. As we are using in complex numbers A plus IB.
अच्छा.
And in quaternions, we are having 3 imaginary numbers. So we are naming as E1, E0, E1, E2. And in octonions, we are having 7 imaginary numbers. So those imaginary numbers are called here fundamental units, corresponding to the that algebra which we are using here.
उसी तरह से वो K1, K2, K15 तक था वो.
Yes, yes, sir. We can. It is about the notation. We can use IJK. We can use E0, E1, E2, or K0, K1, K2.
इनके कोई मतलब कुछ रियल वैल्यूज हैं कि कुछ जो रियल एप्लीकेशन होते हैं कहीं?
Yes, sir. Actually, sir, if we are saying about the quaternions, it is having a very heavier real applications in 3D space, and in as compared to quaternions or complex numbers.
चलो इसमें थोड़ा डिटेल्स में डिस्कस करेंगे. थैंक यू.
Anyone? You have any doubt?
And from the quaternion numbers, quaternion numbers are heavily used in 3D space or mathematical physics.
अच्छा.
It has a very deep study about the quaternions.
Good. Very good.
Thank
Okay.
you, sir.
Again, madam, thank you very much for your
Thank you,
giving
sir.
a nice talk.
Thank you, ma'am, for your lecture.
Mahendra Gupta.
Welcome, sir. Welcome. Thank you, sir.
Ma'am,
Thank you
so
for
much.
this opportunity, sir.
Dear participants, now we will meet tomorrow at 9 a.m. The lecture will be delivered by Professor Ashish Srivastav. He is professor in Department of Mathematics and Statistics, St. Louis University, USA. St. Louis University. So we will meet again tomorrow 9 a.m. Please, you are most welcome. Thank you.
Thank you, sir.
Okay, thank you all of you.